because they're upside down. We built an entire, the first integrated circuit I was ever involved in the design for was a IR imager, the first one optimized for astronomy, and it was all PMOS because the PMOS, no CMOS, because PMOS has lower noise. So in order to get over the difficulties of using PMOS, what we did is we just made the power supplies negative. And so then we could draw our circuits right side up. And I think there, I may have, yeah, okay. So this is the NMOS version of a reference. We want to be able to draw the PMOS version of it. The easiest way to do this, and this is what we did, it meant all of our drivers were negative voltages too. We make this negative 1.8 volts, and we draw the same circuit, but we just draw the transistor upside down. And then the gate goes back wait, we got to do it the other way. I did that wrong. This is the source. The source is at the highest voltage in our circuit, which is ground. This is the drain. So I basically just take that same NMOS driver and I put a negative power supply on it. That works. Sometimes you have to use positive voltages. And in this case, if I'm going to use a positive voltage, 1.8, I'm going to put, notice I'm looking at this so I don't screw this up. I love NMOS, I love PMOS. And the resistor goes there. This is my drain voltage. My VDD is now, oh, yeah, okay, that's the drain voltage, yep. It's at 0 volts. This is the drain. This is the source. And then the gate goes back to the drain. You've got to be careful with these. That's another version of the circuit. This is why I don't like drawing PMOS versions of circuits, because I have to stop. If I didn't have it sitting here right in front of me, I'd be sitting here thinking out loud for quite a while. Okay.
So, do we have to do any calculations with this one? Or?
I usually don't. If we wanted to find VGS, what would we do? The VGS, drain, gate, and source. VGS is going to equal VDS in all of these. It's to the drain. If we know the current, yeah, and if we know the current, we can get the voltage out of it. And it says same ID. So we're given an ID basically here. I've never actually done anything more on the slide than just draw it. Given the same ID, we could calculate VGS using KN over 2 VOV squared. It's the same formula we've been using all along.
Sorry, I just have one last question.
Okay, sure.
Back on example 9, when we found the VGS, that was just for the 2 transistors in the divider, right? Not for the
right.
Transistor.
If we wanted to find the VGS for the current transistor, it would have an ID of 50 microamps. And we would have to take the size of that transistor, because it may be different, and a lot of times it is, to calculate its V over voltage and figure out what voltage we would need on VREF to get 50 microamps.
Okay.
That current transistor on the diff amp is pretty much used as to bias it, to set the amount of current for the whole circuit. And a lot of times what you want to do inside an integrated circuit is you have several of these op amps inside there, and you want the currents to be matched across there. So you would use that current mirror transistor, 2 transistors that we looked at yesterday to match the current from one op amp to another. Fairly easy to do inside an integrated circuit. Okay, I'm not going to talk about that circuit again. I did that in the last class. So I've got a circuit here. We want to look at this. We've got VDD is 1.8 volts. 1.8 volts. We got the VTN. We've got the Kn prime. The W over L is 10, reduces to 10. And our goal is to make VD equal to 0.1 volts. And the first thing I want to do is look at this and say, well, what operating region is this in? Normally, this is a red flag to me. Transistors with small VDS are not in saturation. They're digital circuit switching circuits. In fact, this is what this is. This is a pass transistor. This is something you'd use, like, say you had an Arduino that was operating, or you had an Arduino output, and you wanted to turn power on to a circuit and run it from a separate supply. So the power's coming from here, but the control's coming from here. We'll do this. This is like the first project in 490 in the fall. Control. And that is a series pass transistor. So the first thing is, I'm thinking this has got to be triode, and I know I'm right because I got the notes right next to me. What we want to check for to see if it's in saturation, remember VD has to be greater than VG minus VT. My gate voltage is 1.8, and my VT is 0.4, and the drain voltage is 1.8. Okay, so that is not true, so it must be in triode. To get the VGS, really? Did I really do that? You'd have to use the triode equation. No, we don't know. Oh, we know VD. Never mind. So I plug into the triode current equation, and that looks like this. Kn over 2. There's various versions of this, and they're all correct. Some of them have the 2 on the inside, and some of them have the 2 on have a 1/2 on the inside. And you'll see different versions of it in the Cedra Smith book. VDS minus VDS squared. Let's see, VDS in this case is 0.1. VGS is 1.8 minus 0 is 1.8. And VT is 0.4, that was given. What else do we need? We need Kn, which is Kn prime W over L, 200 micro times 10. And we could plug all that into the equation and come up with 270 microamps. So we got ID, we got VDS, we got VGS. Once we get that ID, did somebody chat at me? I don't know. 270 microamps. We can calculate a value of RD. Just using the voltage drop across the resistor is 1.8. This is Ohm's law, minus 0.1 over 270 microamps is going to give me RD. And what the heck is RD? 6.3 K ohms. Okay. That's called a series pass transistor. It's used to have a small control signal coming from a microcontroller or something like that, control power switching to a motor. Normally, these would be separate power supplies. Okay. All right. I don't like this one. It was like the bane of my existence. Couple of things that we can note here that are very useful is that right here at this node, I have no current going into the gate because it is a MOSFET. And that'll make this problem a little bit simpler. What the heck is my, what did I use? How much of this do I want to do? Okay, so this is 1.8 volts. So this just looks like a voltage divider. RG1 and RG2 form a voltage divider because there's no current going into that gate. RG1 equals RG2. Oh, okay, that's fine. So the voltage we're expecting to see here is 0.9 volts. Now here's the conundrum. I don't know what ID is. The only way I know how to get ID at this point is to find VGS. I know VG, but I don't know VS unless I know ID. So I've got a system of two equations and two unknowns. I can write an equation here. This is VGS. And this voltage right here, VS, would be ID times RS because it's referenced to ground. This forms like a mini KVL loop. We could write a KVL equation here, or you can think of this as I start at 0.9 volts, I drop VGS, and I drop IDRS, and I get to ground, which is 0. So I get one equation. 0.9 has to equal VGS plus IDRS. It doesn't help us a lot because we've now got, we know what RS is. We've got one equation and two unknowns. We need to get a second equation that relates ID to VDS. Uh-oh. What's the other one I know? ID equals KN over 2 VGS minus VT squared. We've got a system of two equations and one of them is quadratic. As much as I wanted to. To solve this, basically what I could do is I could say, okay, ID is 0.9 minus VGS over RS. I could plug in that value here for ID, and then I'd have one equation and one unknown, and I would get two solutions. One of them probably comes out to be a negative number, and I can throw out because there's no negative voltages in this circuit. Okay, I would not, I don't do that. Okay, I'm just not going to do that too. I hate that. This is the reason why when we do the common source with the source resistor, the math gets a little messier. That's enough of that. It's a messy, that's a really messy example. Here's a much simpler version of this. Now I know ID. If you know ID, you can set everything up so it's okay. ID is 0.5 milliamp, and you're given the voltage you want at the drain is 3 volts. So I can easily pick a value for RD. Ohm's law. RD is going to equal 3 minus 0 over 0.5 milli. RD. 13. Page too early. That is 6 k ohms. Okay. We found the value of RD. Now, since we know ID, we can get VGS. VGS is going to equal the square root of 2ID over Kn plus V threshold. Okay. We can get VGS, and we can choose the ratio. Just never mind. I'm doing more than this is what happens when you relax. I'm going to plug these numbers in. VGS is the square root of 2 times 0.5 E minus 3 divided by, in parentheses, 1 E minus 3. And I don't know W over L, so I can't solve for that. What? Oh, it's just regular KP, so you're right, I'm good. It is 1. No. Plus V threshold is minus 1. Oh, we have to take the negative square root because this is a PMOS. No, I'm not frozen. I'm my pen's locking up again. So that would be -1. It would be -2. Okay, so that would be -2. I can only draw my finger now. Volts. Okay, we've got VGS, but VGS is right here. So this is 5. The gate has to be 2 volts below that, so the gate would be at 3 volts. Now I can set up the ratio of RG and RG1 and RG2 to give me a 5 volts, to give me a 5 volt split. An easy way to do this would make this 3 megohms and make this 2 megohms. Just using voltage divider. I usually pick really large values for RG1 and RG2 because all they're doing is setting that gate voltage. And with bigger resistors, I'm going to have smaller current. I'm going to be wasting less power through them. So those are usually megohms, tens of megohms. Okay. Have you seen this circuit before? Does it look like a CMOS inverter? Okay, good. Somebody acknowledge that. We want to match these transistors so they both have the same Kn. Kn equals Kp. In order to do that, I'm going to have to make this transistor at least about 2.5 times bigger than the NMOS transistor. So this will be 2.5 W over L. Oh yeah, you get to do this in the next lab, and this will be like W over L. Okay, that's how I match them. In the magic, I can do that. And their threshold voltages are going to equal. Now, if I put my high power supplies at plus 2.5, so if I put 2.5 on the input, this is an inverter, I'm expecting 0 on the output. Or my 0 in this case is minus 2.5. Now, if I put minus 2.5 on the input, I'm expecting this to invert. Now I have a short to my positive power supply. I'm going to get plus 2.5. We've already been through that. Let's look at the great mystery And this was a circuit we were actually looking at in 490 yet today. I just have to show you. It looked like this. Most people would looked at that and said, what does this do? They said smoke. Okay, no, it doesn't smoke. Let's get something really contrast. Red. So I'm going to put 0 volts here. If I put 0 volts here, then my VGS on this transistor is 0 minus 2.5 is negative 2.5. This transistor's on. I put 0 volts on this transistor. Its VGS is 0 minus negative 2.5 is positive 2.5. So this transistor's on. Both the transistors are on. Where this thing tends to want to be stable at is right at VM, the midpoint voltage. I get 0 point volts on the output. And you can think about this, and I was actually talking about this in 490, why I think you should take 380 first. As you think about the voltage transfer curve for an inverter, when I'm at this, this is my VN, and this is my V out. When I'm at this like VDD over 2 on the input, halfway in between, my output is also going to be at VDD over 2. It is a inverter that's actually operating with both transistors in saturation, and it ends up being in that linear range. And this is why this circuit up here, this circuit here works. If the output is VDD over 2. That's the only stable point for that to operate at. Because VN has to equal V out, which would give you VM. Okay. Now we're going to look at the first generic MOSFET amplifier. This is called a common source amplifier. Let's talk about the general procedure first. We did this in 280. The first thing you do when you're designing it is you pick a DC bias point, and this is often called the Q point. I actually had a senior level class in analog IC design, and I was taking an exam, and I looked through the exam. Every single problem asked me to calculate the Q point, and I didn't know what that meant. So I just said, I'm going to give up. I'm going to wing it. I'm just going to calculate the DC operating point. And apparently that was the right thing to do. Okay. What the important parameters in the DC operating point are big ID, big VGS, big VDS. Find those three. You can calculate all the circuit parameters that you need to. Okay. Then once I do that, I use those ID, VGS, and VDS to calculate the small signal parameters, the little RO, the GM of the transistor, and then I can use those to actually calculate the gain. Now this equation here looks a little screwy, but this is the nomenclature that's in the book. Little v, big G, big S. I know that's the only way I can write them correctly. This one right here is the total VGS. Equals big V, big G, big S. This is the DC part. And little v, little g, little s is the AC part. And that's the nomenclature in the Cedra Smith book, and they stick to it pretty closely. I try to, but sometimes, yes.
And then is that AC port using the gain in the small signal analysis equation, or is that still big BTS?
The gain in the small signal analysis.
The equation just above.
That is little v, little g, little s, or it should be. When I'm handwriting it, I usually just use a little cursive kind of version of a v to say that it's small. That one it's hard to read. Okay, so we got DC and AC. When we're talking about gain, we're talking about the AC gain. What the DC is used for is to set the bias point, to put it at the correct place on that voltage transfer curve. That would be really hard because I haven't looked at the pre-lecture because no one's asked me a question about it. I loaded them in and I don't rework them along with you guys. What was the terms on the pre-lecture?
One of them was total instantaneous voltage.
Oh, okay.
The other one was DC voltage, and then the other one was, I think, signal voltage.
Okay. So this is the, right here, this part right here is the DC voltage. The AC would be the signal voltage. And the total instantaneous voltage would be over here. Instantaneous voltage. Oh, okay.
All right. Thank
Okay.
you, Julie.
Okay, no problem. Yeah, when you do your homework, think about what you need to solve the problem, what kind of mistakes you're making, and fix those. Really think about what you're doing and not just work towards getting an answer or getting the right answer. Think about the process. That will help you on the exam and help you later when you have to actually deal with these circuits. So here is a common source amplifier. I'm putting my signal voltage, because this is my AC plus DC, so I'm putting some DC bias plus some signal voltage plus AC on the gate. So this is my input, my signal or my AC input. My output is this output coming off of right here. It will have both an AC plus a DC part, but I'm taking the output off the drain. So the trick to naming these amplifiers is signal in is on one terminal, signal out is on the other terminal. The AC ground for this is on the source. And another word for source, for ground, is common. So we call this a common source amplifier. Input on the gate, output on the drain, the source is common. Okay. Operating region, I'm given VGS and VDS. So VDS is 1.0. Is that greater than VGS minus VT? Yes. So we're in saturation. And it's not in cutoff because VGS is greater than 0.4. Now, as VGS, the total signal on the gate to source goes up, as VGS goes up, ID is also going to increase. And if ID increases, the voltage at the output will be VDD minus IDRD, will go down. Doesn't sound like a great amplifier because when the signal goes up, the output goes down. But there's a reason for that. And there's signals plotted here. If I actually go and plot the input signal and the output signal, you can see it has two parts to it, and you get to do this on one of the homeworks. My little v, big G, big S, my total signal is a DC part, steady state, plus some AC signal riding on top of it. literally the sum of those two voltages. Different nomenclature people use is, well, of course, this silly equation we've already been over with all the case changes. Now, our signal voltage, our little VGS, little v, little g, little s, is a function of time. It equals some peak magnitude voltage, and that's what the little hat means, is that it's the peak voltage times the sine of omega t, if it's just a simple sinusoidal signal. And notice here what happens when this AC signal's at its peak, this AC signal's at its minimum, just like we argued in the next one, in the last slide. If this one goes down, this signal goes up. And so what you're really getting here is it is a larger magnitude version of the input, but it's got a phase shift. And it's exactly 180-degree phase shift. Plus or minus 180 degrees doesn't really matter. You end up on the same point of the circle. And sometimes we just get rid of the phase shift and put a negative sign out front. It's the same thing. Oh. Okay. I think I took out that slide. Okay, we're thinking about right here where the transistor's in cutoff. If the transistor's cut off, ID is pretty much 0, maybe some leakage current. And if ID is 0, IR, this is they're in series. The resistor has the same current as the transistor. So IR also equals 0. Because KCL tells us that ID equals IR. If I have 0 current, and I start up here at this voltage VDD, and I drop 0 volts across a resistor, this is also going to equal VDD. So we can see for this part of our voltage transfer curve is that when VDD is high and we're in cutoff, that corresponds to ID being 0. Okay. This is also an NMOS inverter too. And the number of slides is always deceptive. Okay. We go into the region between A and B. We go into our linear region. The transistor is in saturation at that point. We still know the current through the resistor has to equal the current through the transistor. So I write the KCL equation. The current through the resistor is VDD minus VDS, its voltage drop divided by its resistance. And the current through the transistor, its ID equation, is Kn over 2 VOB squared. The two of them have to equal each other because they're in series. So I just take this equation right here and I solve it for VDS. I multiply the other side by RD and I subtract off VDD and then I negate the whole thing and I get that second equation. The gain is the slope of that line. It is the rate of change of VDS with respect to VGS. So we've got an equation for VDS. If we take the derivative of that equation with respect to VGS, we get the voltage gain. I don't want to do a derivative because I haven't taught whatchamacallit in a long time. That comes out to be, the 2's cancel out, and you get minus Kn RD times VGS minus VT. So that is the gain. We derived it for that particular circuit, and it works for that particular circuit only. The more general thing is that the gain equals the slope at that point. Now, remember when we did that little thing where I draw a little triangle wave down here and I got a big triangle wave out here? My big triangle wave out here changes the Q point. The slope of the line is different at those different points. And that is one of the things that leads to distortion, because the gain is changing with the signal level, and it will distort your signal. It's not exactly a straight line, but all circuits have distortion. But we're going to pretend for this class it's a straight line. I'm sorry. What's happened to me? I learned the theory and then I integrated the theory with the practice, and I see it all at the same time now. Okay. We've got 3 equations we can use for gain. We know that, well, which one did we look at a second ago? Kn RD VGS minus VT with a negative sign. So this is the one we derived. We know VGS minus VT is just V over voltage, so we can do that replacement. And we can take these 2 equations and mess around with them algebraically, and it turns out this equation is just as good. The point of all this is we got to think about, how do I increase the gain of the circuit? If my gain's too low, what can I do to make it higher? I can increase Kn. I can build or buy a better transistor. I can use a bigger transistor, bigger W over L. I can increase RD. I have choices here. I can make this smaller. Again, that's in the category of buy a better transistor. Or I can increase VGS. Those are the handles that I have on there. And I'm really going to apologize for the next statement, but this is the language we use. Okay, there's limits to this. Now let's say I get so much current, I get so much voltage right here. I make VGS so big that my ID gets so big that this drops down to 0 volts. Okay, I put the transistor, it can't draw, okay, thank you. Is ID for DC or, oh, big ID is DC, little ID is AC. Okay. At that point, I can't go to bring this signal down anymore. It's as low as it's going to go. This, oh, I shouldn't say this. So this, I'm sorry. The word I don't want to say. Okay, so let's say, let me draw a picture. That's probably the best way to do this. Here is my here's my input signal. Here is my output signal. It's large, negative. Now what happens here is, it's beautiful, isn't it? I can't get voltages below, we'll say this isn't 0 volts, but we'll call this 0 volts. I can't get voltages below 0 volts out of this circuit. So what happens is the output actually clips off. And I can't get, if I set the gain too high, I'm going to have a problem. If my power supply is 1.8, I can't get a voltage above 1.8. So it's going to clip off that top part of the wave too. If I make this gain so big that the output becomes bigger than my power supply range, I get this clipping. And unfortunately, engineers refer to that as saturation. You get saturation when the transistor comes out of saturation, because it basically shuts everything down. I'm sorry. trying to find a way to say that. So there's limits. You can't increase the gain beyond a point where it causes the output to get above VDD or below ground, because it will not do that. And you cannot increase you cannot decrease the VDS to the point that the transistor goes out of saturation also. Okay, I've just, so, and I didn't solve this. Why didn't I solve this for you guys? Okay, Alex, this one's for you. We've got a voltage right here. It's a small signal. This is around 0 volts, so it's completely AC. It's small, so it's our input. So this is little v, little g, little s. If I find the equivalent of this with a larger voltage swing on the output, that is also purely AC. So this is little v, little d, little s. Now my saturation equation says that VDS has to be greater than VGS minus VT. So we're expecting big V, big D, big S to be larger. So this is big V, big D, big S. It's a DC part. And then the other one must be big V, big G, big S. The other two signals I have left on there are AC plus DC. You can see they have 4 and 3 have a DC component. They're shifted above 0 volts, and they're also wiggling around, so they have an AC component. The smaller version, the smaller signal here is going to be little v, big G, big S. And this one will be little v, big D, big S. Okay, 2 components. The DC part sets where I am on that voltage transfer curve, and the AC tells me what my signal swing is around that DC operating point. Wow. I am like covering this so much better. So we've got this transistor here, and we haven't figured out how to use the small signal model yet. We just have this equation that works for this particular circuit. We want to figure out, let's see, what do we know? We know VGS is 0.6 volts. That's the DC part. Yes. We know RD is 17.5 k ohms. What else do we know? That's about VDD is 1.8. We want to calculate, ID seems to be the first thing I could do, or V over voltage. V over voltage is VGS minus VT. So I'm given VGS is 0.6, my VT is 0.4, so this is 0.2. Once I get V over voltage, I can find ID and over 2 VOD squared. So 400 micro over 2 times 10 times 0.2 squared. And that is 80 microamps. Normally I have like, I normally teach this, I would hate teaching this in this class. When in a normal semester, I have the whiteboard and I like start at the beginning of the class and I just, I remember I miss my whiteboard. So we've got ID, my big V, big D, big S. Well, I've got a value for RD. So this is just Ohm's law, 1.8 minus VDS is the voltage drop across the resistor, and that equals the current, 80 micro times 17.5K. And we can solve that for VDS. That's the VDD minus IDRD equals VDS, or something like that. That comes out to be 0.4 volts. Okay, what else did I want to know? I wanted to know the voltage gain. And I've got this silly equation for the voltage gain. You can tell I hate that. Kn prime 40, 400 times 10. That would be the Kn part. RD, 17.5. And we've got VGS minus VT is 0.2. We plug all that in to that equation up on the top. We get AV is minus, don't forget the minus sign for the common source. And that is minus 14. Now, if you think about the voltage gain, it's always V out over V in. Okay, but that doesn't have any units. Typically, though, I do this all the time. I see a lot of engineers do this, and it's to differentiate between voltage gain and power gain and current gain, because they are all dimensionless. I just stick units on it of volts per volt. And it's just that reminder, that and the A sub V instead of A sub I for current, or A sub P for power. It's not wrong if you write minus 14, but it's one of those things like not putting the subscripts on the transistor that causes you to make mistakes later on. Okay, I'm getting tired. What happens if you crank up little v, little g, little s? If you crank this voltage up, if the peak voltage goes up, this goes down, and eventually as low as VD, oh, thank goodness, it's just my stylus. As low as VDS can go in this circuit is ground. Sometimes this works, is ground. And so the lowest voltage I can get on VDS is, I'm finger painting again, is 0 volts. Yeah, thank you. Slide 24. Yes, of course. Okay, we'll do that. So if we crank up VGS too high, we begin to clip again, is the basic idea that you get from that. And we talked about that. Oh, yay. Oh, I didn't just have to do this first. Okay. 2 devices in this entire circuit. One is a transistor and one's a resistor. Now, as long as the resistor is behaving like a resistor and you have not let the smoke out, Ohm's law works. So for this resistor, if I have 0 current going through the resistor, if ID equals 0, then that means V out is VDD. I plot that point on this line. ID is 0, V out is VDD. Okay. People used to do this by hand on the backs of envelopes and drive me crazy. I was about 10 years too young to find this useful, but still the old, I don't know. It's still an important, is there still an important point in here somewhere? Now I change colors, purple. There's another thing I can do here. Now let's say if VDS equals 0 volts, if VDS equals 0 volts, then the current is VDD over RD. That's a number, and I can calculate it and plot it on a graph. So VDS is this axis, it's 0, and ID is a number that I calculate. As long as the resistor is behaving like a resistor, the only operating region curve it can follow is a linear one, and it's linear between those 2 points. The actual operating point of this system has got to be at the intersection of those lines. Recall, though, that there's an infinite set of blue lines between each one of those blue lines. There's an infinite set of curves. So if I know VDS and I know ID, if I know the DC operating point, I can find the Q point, and it better be along that line. This is called the DC load line. You may still see this in textbooks. Even people my age don't use this. But it was like a visual tool that you could like put together, because there's certain things in here that if your VDS gets too low, you're in triode region. You've kind of messed up. And you can't operate below a VDS on this on that curve. And if I move VDS out higher, I'm going to get less current and more voltage. I don't know why I put that. I just don't delete that slide. Okay. I could probably do your exam too. I just want problem. Oh, we're out of time. Let's just go. You look at the pieces and you start to divide and conquer. We'll start with this on next class. It's an op amp. It's a 741 op amp. What?
Like with the 741. Or that was just part of the space.
Yeah. Oh yeah. I probably threw that one. This is the one I scare you with. We'll look at the pieces and we'll talk about some of the, there's current sources on here. There's output stages. There's amplifiers. There's all kinds of things I see. Looking at these little circuits here helps you look at the big circuits later on and decipher them. It's time to go. Oh, Alex, which slide did you want? Oh, thank you.
24.
Okay, so, oh great, and it did that thingy. So we're gonna move, everybody move to the left. There it is right there. On one of the homeworks, you actually get to do this in MATLAB. If you need some help plotting things in MATLAB, I'll send you my code. I had trouble figuring it out. That's why I'm sympathetic. But yeah, you get to take various amplifiers and actually plot these circuits like this, plot these signals like this. Okay, good. Okay, I'll see you guys on Friday in lab. Okay.
Hey, Julie.
Yes.
I was a few minutes late, but I was here for the lecture. I'm not absent.
I had everyone marked present. I kind of like, yeah, as I was rebooting my computer, I checked roll again.
Great. Thanks so much, Julie.
Okay, no problem.
See you tomorrow.
Okay, bye.
I have a few questions about
Okay.
like why
Oh, okay. So this is worth, if it's not the right formula. What you're missing here was you're missing the channel length modulation.
I didn't ask.
I know.
That's why I didn't use it. I was making sure multiple times. That's
Okay.